survived the first 11 modules. This is the final one. So our final module will be presented by Professor David Kaplan from the University of Wisconsin at Milwaukee. And David is using many different radio telescopes over his career, including VLA, ASCAP, ATCA, what's the list? Etc.
Yeah.
So, yeah, David, please take it away.
Yeah, thanks. So what I'm going to talk about today is it is similar to what you've been doing in that we're going to be dealing with time series data on a transient event. It is different in that we'll be talking about data at radio wavelengths, but for most of what we're going to actually discuss, you can completely ignore the radio side of it. So that's good and bad. If you're really hoping to learn how to reduce VLA data, 1 hour is not going to be quite sufficient. But if you're looking for more general techniques to learn to use to understand time series data or data analysis in general, hopefully you'll learn some things here. So what we're going to talk about today is we'll go briefly over how radio emission differs from optical emission and how radio observing and data analysis differs from optical data analysis. But what we're really going to focus on is just learning techniques for fitting models to data. And hopefully if we get there, we will add some physics back in, we will interpret our results, and we will see how the analysis we've done enables us to infer properties about a kilonova explosion. So if you've taken an astronomy course, you've probably seen a plot like this with the radio spectrum, and you probably saw all these different little breakups of the radio spectrum. There's radio, there's microwaves, there's all these different things. From the point of view of somebody working on this field 30 years ago, maybe those mattered. But from the point of view of people now, they don't matter at all. So basically, all you need to know is that from about 3 kilohertz on this plot, or if you're looking out into space from a frequency of about 10 megahertz, all the way up to about 300 gigahertz, we can call it radio astronomy. And the main distinction with radio astronomy compared to other types of astronomy is that you are sensitive to the phase of the electromagnetic waves. Sort of like in gravitational waves that you talked about a couple of days ago, the phase matters. So in the optical analysis and X-ray analysis, all you're seeing are photons, little bundles of energy. Radio analysis, you're actually coherently sampling the electromagnetic wave. You can get the frequency, you can get the phase, you can get the polarization, and those all matter. Now, the exact way that the radio telescopes do that, we're not going to go into. But in general, all the stuff you can consider in some general basket of radio astronomy, and the same techniques can be used over that whole span. Brad already talked a little bit about non-thermal emission. What we're going to look at later is radio emission from a kilonova, 170817. And to understand what we're seeing there, the optical emission from that kilonova was predominantly thermal, hot gas, radiates like a black body. If you have enough information, you can see spectral lines, figure out what it's made of and things like that, but it's basically, hot stuff radiates because it's hot. Radio emission, on the other hand, like the non-thermal emission that Brad was talking about, is coming from relativistic electrons, very energetic electrons that are all spiraling around magnetic field lines. So we call it synchrotron emission. Relativistic electrons, they spiral around magnetic field lines. Each individual electron has a spectrum sort of like that, but when you add up a whole bunch of them, you end up with a spectrum like that, you end up with a power law. So like Brad mentioned earlier, same as in X-ray, same as in radio, power laws are pretty ubiquitous. The non-thermal emission can be described by a power law. The flux is proportional to the frequency to some exponent. In the particular case of the kilonova, what we have happening is a shock wave. You have a relativistic jet of electrons, and it comes out, moving very close to the speed of light, and hits the surrounding interstellar medium. When that happens, you get a shock wave. The electrons get quickly decelerated, and they dump a lot of their energy into this synchrotron emission. So the radio emission that we ended up seeing from 170817 is consistent with this picture. So what we're seeing here is the light curve. It's the flux density, the brightness of the radio source is a function of time. And you see a bunch of points. They are labeled by the different telescopes that we observe them with, and they have a number of different models. We'll get to the models later. But the important things to look at are that the emission, we believe, is optically thin. It means it doesn't block itself, which is important for how we interpret the spectrum of the emission. And the emission spectrum doesn't change across over a year, almost 2 years of observing. We actually haven't been able to detect it in a little while. It's too faint right now. Hopefully we'll be able to pick it up again soon. But for all the time that we could detect it, the spectrum was the same. So it was the same power law over years. So it's not like the optical emission that was very hot and that cooled down quickly, but it was just the same power law the whole time. And by analyzing the radio data, we're not going to be able to do all of this today, but by analyzing different radio observations together, you can figure out the opening angle of the jet. Was the jet narrow? Was it wide? We can figure out the angle of the jet to the viewer. Was it pointed right at you? Was it pointed at 90 degrees? We can figure out how dense was the interstellar medium around where the explosion happened. And we also can determine the total energy of the explosion. These are all very fundamental things. X-rays, it turns out, are also giving you the same pieces of information for this particular explosion. But in this case, the radio data were more powerful because we could observe it a lot more. So here's a cartoon that you've probably seen. The radio emission is coming from when you have this relativistic jet coming out and hitting the interstellar medium. In particular, figuring out the angle between the observer and the jet is very important. It enables you to determine the Hubble constant. You can compute the source distance directly from the gravitational wave strain, but the distance is highly degenerate with the inclination. You don't know, is it face on and further away, or tilted and closer to you? If you could figure out one or the other, then you know the distance, you know the redshift of the galaxy, and you can determine the Hubble constant. So when they tried to determine the Hubble constant using gravitational waves alone, they got this big orange curve. You see it has a big fat tail out to very high values of the Hubble constant. But work by Kunal Muli and collaborators showed that using very long baseline interferometry measurements of this jet, they could determine the angle of it relative to the observer. They came up with this very nice, tight blue constraint for the Hubble constant. It's still not as good as other measurements of the Hubble constant are from things like type 1a supernovae, but the hope is that over the next 4 years, it will get a lot better. So that's why we want to look at radio. How do we look at radio? Well, you're all probably familiar with the diffraction limit. The resolution of a telescope, any telescope, is fundamentally limited by lambda over d, telescope wavelength, telescope diameter d, wavelength lambda. Now, radio telescopes, they don't have to be polished glass. They can be pretty big. You know, we have fully steerable telescopes that are 100 meters across, and even bigger telescopes that are up to, anybody know the biggest current single pitch telescope? 500 meters. And what's it called?
It's in China, but I don't know that much.
FAST. Yeah. 500 meter aperture spherical telescope. Yeah, 500 meters. So here I took 1 meter, I took 6 centimeter wavelengths, and you get a resolution of only 2 arc minutes. That's not very good. Remember that a typical seeing limit from the ground, that's not even the diffraction limit, just the seeing from the ground is about 1 arc second. So you're a factor of 100. That's for a 100 meter telescope. We can't currently build a 10 kilometer wide telescope, which is what you need in order to match ground-based resolution. But we can break our telescope up into multiple pieces. If you take 2 smaller telescopes, separate them by a distance b, which can in principle be anything you want, and then hook them up to a powerful computer, you can turn that into an interferometer. And that's why most radio telescopes look something like this. Many smaller dishes. It's a lot cheaper. You end up spending more money on the correlator, silicon computing, but these days Moore's law buys you a lot of computer, and less money on the steel to make the dishes. So, for instance, if we have the same equation, we can now separate our telescopes by 10 kilometers and we can get back to a 1 arcsecond resolution. So radio observing is good. It can be done during the day. You can be, observing from your desk during the day while you're, at classes or all sorts of stuff. You don't have to stay up all night. Or you can have your friends in Australia observing during their night, which is your day, if you're, busy at a baseball game or something like that. The emission isn't absorbed by dust and gas in the interstellar medium. So unlike what Brad was talking about, where the softest energies are really absorbed by the ISM and you can't see them, radio waves basically transparent. You can see all the way through the Milky Way galaxy, other galaxies as well. And the nice thing is, at least in this particular case, the emission evolves slowly. The optical and ultraviolet emission from the kilonova peaked before we got onto it after 12 hours, and then was all gone by a week. The radio emission we didn't see for 2 weeks, and it evolved slowly. It peaked after about 5 months. That meant that, the lifestyle of Dougal, who was doing the observing, was a lot more relaxed. He didn't have to stay up all night, every night, analyzing, reducing new data, and adding it into the FITs. But there are challenges for radio observing. The biggest challenge is this: radio transmitters, radio frequency interference. A cell phone on the moon would be one of the top 2 or 3 brightest radio sources in the sky. And every time the federal government gets, a $5 billion auction to get a new portion of the radio spectrum devoted to controlling a new type of widget, that makes radio astronomers cry. Radio telescopes also don't get normal images. So you guys did some good image analysis earlier in the week, right? You started with raw images. They had all these weird artifacts. You had the flat field and all this stuff, but you pretty quickly, even right away you could see, hey, there's a star there, and there's another star there, and you could pretty quickly get to something that was, astronomical quality. Radio telescopes, because they're split up into all these pieces, don't come out with images right away. In fact, what we measure is the Fourier transform of the image. So some of you are probably familiar with Fourier transforms, but we don't only measure the Fourier transform of the image, we measure bits and pieces of the Fourier transform of the image. So when you try to figure out what the actual image looked like, there's missing information. That missing information leads to artifacts in the image. You don't really know what's there. You can make guesses. You can try to say, okay, well, it probably looks sort of like that, or it probably looks sort of like that, but ultimately it's missing information. And you have to figure out some way to put it back. So that means that what you think should look like a nice, simple dot, a point source, ends up looking like this. It has these big stripes around it. You have to find some way to get rid of those. Now, we generally know how to do this, but it's not super straightforward. And that's why we're not starting with raw data from a telescope right now. Now, this missing information isn't just an issue in radio astronomy. It happens in optical astronomy too. Anybody know what it's called in optical astronomy, the missing information that leads to image artifacts? It's the diffraction limit. You can think about the diffraction limit as you're only sampling a finite space of the Fourier transform, and then outside that, you don't know what's happening, which means that you have a limit as to how sharp your source can be. It's the same thing. We have the diffraction limit in radio astronomy too, but we basically have a whole bunch of other gaps in our information. And just what I was mentioning before about the US government auctioning off different parts of the radio spectrum. This is the radio spectrum as defined by the FCC currently. You can't read any of these things, but you could see all these different pieces, all these different colors are different pieces of the spectrum used by, ambulances, Air Force, radar, cell phones, wireless gadgets, everything. So we need to squeeze ourselves in here. But as I mentioned, when you're doing radio observing, you're measuring the whole electromagnetic field, which means that you have information on the polarization, and you have spectral information, and you have high time resolution information that are all present there. Unlike in, say, optical observing. Optical observing, you choose a G-band filter. And you can't tell within your G-band filter whether it's blue or red. It's just, it has a G-band magnitude. In radio observing, if you have enough signal to noise, you can tell what the spectrum is. You can tell what the polarization is. So here are some observations we did recently. We were looking at flares from a nearby flare star. And what you can see is that instead of having just the total flux over a bandpass, we were able to break it up into 1,000 little channels and also look at the polarization. And you can see that this flare star had these weird polarized flares. Basically, we're seeing an aurora around another star. So you can do all sorts of good stuff. Now, it turns out that when you're looking for really faint things, this doesn't matter so much anyway because you're mostly limited by signal to noise. But hey, if the source were brighter, you'd be able to get more information. Any questions about radio astronomy in general? This has been, super quick. Yeah?
This question about RFI.
Yeah.
Recently, Elon Musk released the Starlink satellite.
Yes.
Which of the missions are going to be affected? Will there be
Let's see. They are K-band, if I remember, which is above where I do most of my observing. So I mostly look at sources that are brighter at lower frequencies. But for people who care about star formation and warm gas and dust, they're not going to be thrilled. Yeah, I mean, in general, he's screwing over a lot of astronomers with that. Google Project Loon isn't great either. We can actually see these are these big balloons to deliver internet across the world, and they will both have their own radio emission, and they also reflect radio emission. So you might have a radio station hundreds of miles away. The radio emission will come up, bounce off the, and then come down to your telescope, even if your telescope is located in a very remote area. Any other questions? Okay, so what we're actually going to spend time on today is model fitting radio data. So we're going to compare data to a model. Probably many of you are familiar with this. What we do is we define a quantity called chi-squared, which I misdefined. I forgot to square it. But in principle, you need to put parentheses and a squared around that whole thing. But it's the data minus the model divided by the uncertainties. And the model depends on some parameters that you want to get out. You want to know what is the underlying model that describes your data. So you would vary your parameters to get the smallest possible value of chi-squared. And in simple cases, you can do this analytically. If you have a simple model, you can just take derivatives of this chi-squared with respect to all your different parameters, set those equal to 0, solve them simultaneously using any of the number of techniques that you know, and you get out your best fit numbers. So that's easy. But most models are not that simple. And in most cases, you have to do this numerically. And there are a variety of techniques that are available to do this, and we're going to use 2 of them today. The simplest, most naive one is one that we're not going to do today. That's where you basically just set up a grid of all your different model parameters. Say you have 2 parameters, and you have a 2-dimensional grid, and you just sample every point there, figure out what chi-squared is at each one of those points, and find the one that gives you the lowest value. That's pretty easy to do. 2 dimensions, not too bad. But when you go to 3, 4, 5 dimensions, that ends up consuming too much of your computer time. So there are more clever ways to do it, and we're going to do 2 of them today. Hopefully. So we're going to start with something which is sort of a canned way to do a numerical fit, and that's Python's curve fit. And what that basically does is you give it a starting point, and it always tries to find a way down your chi-squared to get to the bottom. So it's pretty good. It works pretty well, but it's not perfect. One is that it can get stuck at a local minimum. It can find its way down somewhere, and that can be a pretty good solution. But what it doesn't know is that there's another good solution a valley over. So it can get stuck there. It can also be slow if you have a lot of parameters, and it does not necessarily incorporate other information you might know about the parameters that you're fitting. You might know that for A, your parameter, it's more likely to be a big number than a small number. Or maybe it has to be 5 times another one. When you're doing this curve fit, you have no way to incorporate that. But in the technique we'll hopefully get to at the end, we can incorporate that. And that's what's known as a prior information. What we ultimately want to do is sample the posterior distribution function of chi-squared as a function of all of our parameters. That's basically the probability that our data were generated by this particular model as a function of all the different parameters. So here's an example. This is from some work on the data that we'll look at later as a function of 2 parameters, the peak time and some delta 2, which is a slope of our power law. And in this case, we actually just did do a naive grid. We just set up a big 2-dimensional array and computed the value of chi-squared at every point in the array. We found that at this point was the lowest point. Everywhere else it was higher. That one worked okay. But if we're trying to do this better, we need to use a more complicated technique. So we have Python's curve fit. If we're trying to do something a bit better, a bit more robust, that can deal with even higher dimensions of data, or that can deal with prior information, we might want to use a Markov chain Monte Carlo. So an MCMC, or Markov chain Monte Carlo, is a way to explore multi-dimensional parameter spaces. It's used for curve fitting, it's used for integration, and a whole bunch of other things. And what it really does is it puts the sampling where the data demand it. So in our grid, we set up this nice big grid to make sure we got all the way out in the tail of our distribution. But we were measuring chi-squared over here, and the data don't want us to be there. And we're measuring it over here, and the data don't want us to be there either. What's better is that we put a little bit of time over here just so we know that we can ignore that part. And we spend much more time sampling the data up in here. You basically let the data tell you where to go. You let the computer spend all its time doing the interesting stuff and ignore the boring stuff. And it does this somewhat randomly. It will jump around a little bit. It will say, go, okay, around here. Then maybe I'll jump over here. Then actually I don't want to be there. I'm going to go there. But it ends up populating this quite well in the end. So we're going to use this for fitting. It's also used for other types of exploration of multidimensional data. The name comes Markov chain, means each sample that you determine comes only from the sample before it. It has no long-term memory. And Monte Carlo is because we're using random numbers to sample it. So you can do a simple Monte Carlo calculation. You flip a coin, figure out how many heads, and you can estimate the value of a half. Clearly, the more times I flip it, the closer I'll come to half. You can do other Monte Carlo experiments, right? We can draw a circle, throw darts at it, and use the number of darts inside and outside the circle to estimate the value of pi. Those are 2 pretty simple Monte Carlo things. You combine these 2, and you end up with a very powerful way to explore data. We can efficiently sample multidimensional data sets, 10 dimensions, 20 dimensions, not really a problem. And we can incorporate prior information. Now, there are subtleties. You got to make sure you do it right. And we're going to do some of those tests if we get there. You need to make sure you use enough random samples, right? If I try to estimate the value of a half, I only flip the coin once, I'm not going to do it super well. You need to make sure that your final answer isn't determined by where your initial random number started. But if you do those 2 things and you use some basic checks, you can use these MCMC techniques to do lots of really interesting stuff. Now, rather than make you write your own MCMC sampler, which is actually a very good exercise, I encourage all of you in your copious free time to go home and do this. We're going to use a very popular one called EMCEE, the MCMC hammer. And this was written by people who have a pretty good idea of what they're doing, i.e. not astronomers. And is quite fast and powerful. We're not going to worry too much about the details on the hood. There are a lot of things you can tweak in terms of how this works. We're not going to worry too much about them right now. But one thing we are going to do is we are going to try to make some corner plots. So remember, we're trying to look at a multi-dimensional parameter space. Now we have this two-dimensional parameter space here, and you can see that the best fit value for t peak depends on the best fit value for delta 2. If delta 2 is minus 1, then t peak is 130. But if delta 2 is minus 3, it's closer to 170. That means that the best fit values of those two parameters are correlated. And this is for a two-dimensional exploration. If I have, 10 dimensions, I need to look at a 10-dimensional correlation. That's pretty hard. Humans aren't good at that. What we typically do is just break it up into a lot of two-dimensional correlations. So this is called the corner plot. Many of you have maybe seen these or made these yourselves. And what we do is we basically look at all the different possible pairs of parameters. So this parameter is plotted against this, and this, and this, and this, and this. And you can see that some of these are roughly round and circular, suggesting the parameters don't have much correlation. The best fit value of one doesn't depend on the best fit value for the other. But some of them are highly correlated, like the one we saw before. So here you can see, if I pick this one here, it leads to that parameter there. If the best fit value, you can't really read it, but this is actually delta 2. Delta 2 is here, then the best fit for t something or other is around there. Whereas this one isn't really correlated, right? No matter what I pick for this y-axis, the x-axis best fit is always going to be there. So we're going to try to make a corner plot. Hopefully we'll get there. And then a word on units. So radio brightness is measured in Janskys. 1 Jansky is 10 to the minus 26 watts per meter per hertz, or 10 to the minus 23 ergs per second per centimeter squared per hertz. It really doesn't matter for what we're doing today. The numbers that are going to be in the table that we'll look at later have units of microjanskys. It really doesn't matter. Bigger is brighter, unlike magnitudes. It's all you really need to know. It's worth noting these are spectral units. It's flux per bandpass. If you have more bandpass, you get more flux, more energy out. I think that was also discussed in some of the optical lectures, but it doesn't really matter. Okay, any questions? Okay, we can get to the notebook.